Good afternoon, ladies and gentlemen. I'm happy we have a full house. We were struggling to bring people in. I think he was doing a great job trying to bring people in. I'm fortunate that most of the people are back in the room. I'll try and keep it very simple and interesting. I don't want to bore you with too many, slides and presentations. Essentially, the topic for today is, how are enterprises today using digital twin to engineer some of their most sophisticated and some of their most complex products, right? So that's the topic. I have about 10 slides. I should be done in 15 minutes. I promise you I'll take only 15 minutes. So before I get into the topic, I quickly want to talk a little bit about what we do as a company so that you can all relate to what we're talking about. So we're leading the convergence of computational science and AI with engineering. So that's the unique thing about Altair, right? When we mean computational science, in our words, we essentially mean physics simulations, high-performance computing, systems modeling, and AI. Okay, we're trying to bring all of these technologies together to build and deliver the products for the future. Okay, our software and solutions help our customers deliver some of the most advanced, sustainable, safe products by reducing material usage, reducing cost, and making it sustainable and environmentally friendly. So this is essentially the mission statement as stated by our founder and CEO, and we are all fully committed to this statement. You will see how we are doing this as we move forward in the presentation. If I were to talk about the solutions, I already mentioned physics simulation has been the foundation of Altair for the last 40 years, from the time the company was founded. So we can pretty much simulate every physical phenomenon that you can think of. How is the air conditioning in this room? Can I model it and simulate it? Yes, I can. How is the acoustic in this room? Yes, I can. Any physical phenomena in the automotive industry, whether it is safety, cabin comfort, noise and vibration, durability, life, electromagnetics, communication, vehicle dynamics, you name it, we have a solution for all of these. Okay? The second technology that we bring is high-performance computing, which is a foundation to the simulation technology because this is very, very computationally intensive. You require a lot of computational resources to model all of these and run them. So it takes a lot of time and you need powerful computers to run them. So we bring solutions for high-performance computing. The third area is an area where we have made close to $1 billion of investments over the last 5 years, and that's in the area of AI. Okay, we see AI influencing and playing a role in everything that we do today. So our CEO consciously made a decision to make big investments, and we almost invested about $1 billion over the last 5 years to bring in a lot of advanced AI technologies into our portfolio. And all of this is backed with years and years of consulting experience. So a company was founded by engineers who came out of the big three in Detroit, and so they understand the automotive industry extremely very well, and it runs as part of our DNA. And we have a very strong consulting and services team which has been helping a lot of our customers deploy some of these technologies very effectively. So coming to today's topic, what do I tend to address in the next, say, 12 minutes or 13 minutes? What is a digital twin? How do we make one? And where it can be used? So these are very simple questions that I'm trying to answer. We did a survey very recently. This was a survey run by Altair last year, and we interviewed about 2,000 people across different types of companies, businesses, industries, and 71% of the respondents said they were all investing in digital twins. Okay, I'm sure most of you here are investing in digital twins, right? So my job is to help you understand how we can make this simpler for you as we move forward, and how you can get the benefits of these investments. So this slide, kind of goes back to 1980 when the company was founded, and how various technologies have evolved over a period of time. Essentially, these are technologies which are enabling us to build digital twins today, and how these technologies are evolved. If I talk about simulation in the 1980s and 90s, it was more of a forensic tool. People used to use simulation to understand why a part failed, or why a certain failure happened on the field, or when an asset is operating. In the 90s and up till 2000, simulation was a verification tool. You didn't want to build prototypes. You wanted to simulate a lot of things, reduce your prototyping, get a lot of insights before you actually go and build the prototype and test it. As we came close to 2000, simulation became a design tool. A lot of things are today designed with simulation. You build a simulation model before you even build a CAD model. That's the way the industry has moved over the last, say, 20 years. And what we saw in the last, say, 3, 4, 5 years is there is a new stream of design, and that we call that data-driven design. So a lot of design decisions are today taken by using historical data, right? So, and all of these technologies, when they come together, is what enables us to build so-called digital twins. So this is an interesting example, This is very complex, at the same time extremely simple. We all know our bodies, right? So we have a physical body, which comprises of the body itself. The human being essentially comprises of the body, the brain, and the nervous system. These are three different components which helps all of us function. This is an extremely complex and sophisticated product. The most sophisticated valves, the most sophisticated communication, the most sophisticated sensors are all here. And we are all trying to mimic this with all the products that we are trying to develop today, right? How would we represent this in the form of a digital twin? It was a very interesting exercise that we did, right? So the body essentially is nothing but a highly complex mechatronics, multiphysics structure, right? You have bones, you have muscles, you have so many things. So the body can be represented in the form of a highly complex mechatronics and multiphysics structure. The brain is the control system, which essentially sends the signals, and sensors and control signals essentially replicate the behavior of your nervous system, right? And when we bring all of these together is when we build a digital twin of a human being. These exercises are already on. There are people doing research on trying to build digital twins of human beings so that they can predict a lot of health issues, catastrophic, cardiac arrest, and many other issues related to human health. So if I have to define a digital twin in simple terms, for the layman, where all do we use digital twin today? It supports decision making during the development phase. So any simulation model that we have been building for the last 40 years can be called a digital twin, right? We're trying to replicate the behavior of a physical asset in a digital form by using simulation. But that is an idealistic model. It's not a real model. It's very idealistic in nature. You're assuming that everything works perfectly fine, and then you're trying to build a model, right? It helps optimize the performance of a product during operation. If a product is in operation, you can figure out how to improve the performance of the product. And it provides a feedback loop to the people who build these products in terms of how this product is being used, what profile of people use it, how do they use it. For example, a scooter, a guy who does e-commerce delivery would use a scooter very differently from someone who is dropping their child to school. It's the same scooter, right? The way they use is very different. So you can get a lot of insights on how different segments of societies use many of these products. And that can become a feedback loop for us to keep constantly improving the performance and the requirements of the customers. So this is essentially a definition of a digital twin. And as I mentioned, we have design digital twins, which is used in the design phase. We have production digital twins, which are used during production. And we have operational digital twins, which are used in service, when your product is actually on the ground operating under real conditions. So these are three different twins. This is how everyone used to look at digital twins in the past. But what we are trying to do is collapse all of this into one single model. And we call it one total twin. Okay, a twin that can support you across the entire life cycle, from the time you conceive a product to the time you take it to the scrapyard. Can I build a digital twin which supports all of these? That's essentially what we've been doing at Altair. And I'll show you the building blocks of this digital twin. What are the technologies, backend technologies, and how do we go about building this twin? So essentially what you look to the left side of the screen is the digital twin. It's digital. And what you took the right side is the physical twin. It's all physical, right? You have the actual physical asset, you have sensors, you have devices mounted, information is constantly being collected and streamed. And what you have on the left side is you're trying to exactly replicate the behavior of what you have on the right side by using different types of physics. It can be mechanical, thermal, electrical, hydraulics, control systems. You're using different types of physics to build a systems model which exactly replicates the behavior of a car. Right? A car has all of these. And what are we trying to do? We're trying to collect data from the car, okay, by using all kinds of sensors, devices which are mounted on the car, and we are feeding all this data back into the simulation model. Okay, so the simulation model starts exactly mimicking the behavior of the physical model. If I build a normal simulation model, it would be very idealistic in nature. Right? If I have to have it exactly mimic the behavior of an asset which is running on the field, then the feedback mechanism is very important. Like a car which is brand new would behave very differently from a car which is done, say, 50,000 kilometers, right? That's what we are trying to understand here. At 50,000 kilometer, how does my car function? Or at 500 cycles of washing in a washing machine, how does the washing machine behave? So we are actually going in time. It's a time traveler. You can go ahead, you can go behind, and you can figure out how a system was working at a given point in time. So that's essentially what we are trying to do. And what you see in the middle is all the enabling technologies for a digital twin. It can be 3D CAE, which is computer-aided engineering, system models, IoT, data analytics, machine learning, reduced order models, so on and so forth. And a lot of AI and ML is going into building these digital twins. In my subsequent slide, I will show you how AI is being ingested into digital twins to make it more intelligent and being able to reduce the size of the problem, do a lot more simulations, get a lot of insights very early in the process. So this is an example. Since this is around e-mobility, I thought I should take up a few examples related to electric vehicles. So this is a model of a battery, okay, an electric vehicle battery, on which we have been running a lot of simulations. It can be thermal simulations for cooling, it can be structural simulations, it can be various types of simulations. And you can do what we call as design of experiments, which means you run a series of simulations and essentially create a lot of data, synthetic data. Either you can use historical data, which is available from previous simulations, or you can create synthetic data in real time by running design of experiments. And using all of these data, what are we trying to do? We're trying to train a machine learning model and build what we call as a reduced order model. A reduced order model is something which exactly is able to predict the behavior of the battery based on historical information and the information that you have generated. This information could be test information, test data, it can be simulation data, it can be any kind of data, or data coming in from the field for failures. You can use all of the data and build what we call as reduced order models. And these reduced order models are essentially embedded into the larger systems model. What you see at the left bottom side of the screen, that's the larger representation of the car, and that representation of the car has a block in it, which is the battery, and that battery has predictive capabilities. It can in fact predict what is going to happen to the battery. So we're creating digital twins which have predictive capabilities, which can learn on itself from historical data, current data, refine itself, and it's a highly sophisticated piece of software. So how do we keep on improving the quality of the digital twin? How do we make sure that it is more accurate, right? That is one of the things that all our customers keep asking. Okay, you built a digital twin, how accurate is it? Can I take decisions based on what you have built? Yes, you can, provided you have a lot of data, right? So when we are trying to build a digital twin, we are trying to ingest data from the shop floor, which is manufacturing data. We're trying to ingest simulation data, field logging data, warranty data. So all of these data is being fed into the simulation model, which means it's not just one source of data. We are getting data from various sources, ingesting all of that into the simulation model to create one total twin, which is fairly accurate. I wouldn't say extremely accurate, fairly accurate. The more the data you feed in, the more accurate it gets, and it keeps learning with more and more data that is being ingested into the system. This is an example of a brake. If you see on the right side, again, you have the hardware. If you see on the left side, you have the digital twin. And what we are trying to do is, there are 2 or 3 parameters that we are trying to, there are 2 or 3 parameters that we are trying to measure here. You are measuring the disk speed and the brake pressure, and these are being fed back into the simulation model as inputs into the digital twin, and we are essentially predicting the brake disc temperature and the brake energy. Okay? Otherwise, you would have put actually 2 more sensors on the brake to measure the brake disc temperature and the brake energy. So we are actually replacing a physical sensor with a digital twin model. It's very difficult for a brake disc temperature sensor to be put in because it is operating under very harsh conditions. Very high possibility that it will fail in a matter of time because the temperature is so high. So we are replacing that with a digital twin model, which is able to calculate the brake disc temperature from a few parameters that can be measured from the brake. So there are various cases like this where you can build digital twins to predict many parameters where you cannot have sensors placed because of the limitation that it has. So this is a case study or example from a company called Switch Mobility. I am sure many of you know Switch Mobility. It's a subsidiary of Ashok Leyland. They build electric vehicles. Switch Mobility is a customer of Altair. They built a digital twin with the Altair support. And I will leave you with a short video which explained to you as to what they have accomplished and what they have done with our technology and our consulting.
Switch Mobility considers itself as a mature startup. It formed from electrified section of Ashok Leyland and Altair in the UK. Range prediction is the hot topic. Since the battery electric vehicles doesn't have as much range as internal combustion vehicles, we needed to understand which parameters affect the battery range and its performance most. Altair's responsibilities with the project was delivering proof of concept simulation work which has alignment with the real life data. For that, Switch needed to supply as accurate data as possible, especially for our in-service vehicles and the real life applications. We supplied them to Altair, and Altair used those data to create the simulation aligns with our real life data. When all that comes into place, you basically generate a new system including all the subsystems to basically create a digital twin of the in-service product in the simulation world. Before we start with this project, we were expecting mass will be one of the vital parameters that we need to focus on. But apart from that, we were a little bit unclear how much the aerodynamics or the rolling resistance will affect. So this project helped us to understand relatively with the higher and lower speeds which parameters comes into place and which one of those have the most influence to the range itself. If you know the range confidently, that will give you confidence before you building the prototypes and doing the physical test. And rather than doing that, you can just simulate your vehicle with live data, and you confidently eliminate a couple of prototyping activities and use of real tests. That saves time and cost, of course. We used the outcome of this project as our starting point for our next generation buses and the LCVs. So basically we will have the confidence that we can predict our range as accurate as possible and more than 90-95% accuracy, and show this confidence to the customers that our new products will have the same level of accuracy and give them to reliability of having the projected range will be very similar to the real life driving conditions. Altair has really wide range of software capabilities and engineering support. This is one of the most important parameters you consider when you are working with an engineering partner, because in some of aspects you won't have the answers and you need support, and that's where Altair comes in. We really enjoy working with Altair since we started our partnership back in 2020. So in that sense, I'm confident enough to say we are going to increase our cooperation and it will grow stronger in oncoming years.